Hi, today I'd like to make some thermite. Thermite is one of the most energetic reactions known to science. Here's the balanced equation for a typical thermite reaction using iron 3 oxide along with very fine aluminum shavings. I'll need to wait for dusk for the best viewing, but last things first, here's a clip of us setting off 100 pounds of thermite. Enjoy! There's a lot that we can dig into because thermite is a very interesting substance. Let's start with some numbers. Depending on the fineness of the thermite mixture, it has an ignition temperature somewhere around 3000 degrees Fahrenheit, and once it starts burning, it burns hot, around 4000 degrees Fahrenheit. For comparison, the surface of our sun is sitting just shy of 10,000 degrees Fahrenheit. Once the reaction is going, there's pretty much no stopping it. Unlike normal fire, thermite does not require oxygen in order to burn. Well, it does, but not from the air. Did you know that there are actually several different mixtures for thermite? The one that people are most familiar with, and the one that I'm going to use here today, is a mixture of aluminum and iron oxide. So here we have the chemical equation. We have iron oxide and aluminum yields iron and aluminum oxide. The oxygen is always seeking the lowest potential energy, which would be to be bonded to the aluminum. However, it's already bonded to the iron, so that's where the heat of ignition comes into play. It needs a little extra energy to leave the iron so it can go to a lower potential energy bonded to the aluminum, and doing this it releases energy in the process. Once the reaction begins, it gives off light and heat, more than enough to start a chain reaction. To figure out exactly how much energy is being given off, we need to know two things: the balanced chemical equation and a table that shows us the standard enthalpies of formation for the compounds that we're using. We find that the standard enthalpy of formation for iron oxide and aluminum oxide are 822.2 and 1669.8 respectively. We don't consider single elements in the enthalpy of formation. The negative sign before these numbers means that that energy is being lost to the environment, and we can figure out how much energy by summing the enthalpies of formation times the molar ratios, which yields about 847.6 kilojoules of energy. Our reaction is very similar, however instead of using iron 3 oxide, we used iron 2,3 oxide, aka magnetite, a type of iron ore. It's important to know which kind of iron oxide that you're using because it'll change the molar ratios in the balanced chemical equation. Now the ignition of thermite is actually the tricky part, because not much short of an oxyacetylene torch is going to be enough to kick the reaction going, and show of hands, who has one of those lying around? Our first idea was to use a slow burning flash powder, a combination of aluminum powder, potassium nitrate, and sulfur, the latter of which can be purchased at any gardening store. Perhaps I'll do another video later down the road and go into this in more detail. Normally this method would work just fine, however the aluminum that we were using was very coarse, and thus it required a higher ignition temperature. So what we ended up doing is making some finer thermite that would ignite at a lower ignition temperature, and the heat of that would be stepped up to the larger thermite reaction. In order to ignite this finer thermite powder, we used a sparkler. A magnesium strip would also probably work just fine. You may have noticed that the fine thermite powder is a little more explosive than the rest. Size and surface area of these particles has a lot to do with the speed of the reaction. Now typically thermite is not explosive, however there are some ways that you can get it to release its energy a lot faster. You may have noticed that when the thermite started burning through the bottom of our steel bin, there was a strange green flame. That actually wasn't caused by the thermite. Although we were a little confused for a little bit, it turned out that the steel bin we were using was galvanized, covered in zinc, and when zinc burns, its flame is a brilliant green color.
Yeah. I gotta spend a burning thing. Do you want a penny tank?
Ready?
Here we go.
Literally burning.
Happy New Year!
Well, your wish won't come true.
That's fine.
Remember that thermite burns at around 4,000 degrees Fahrenheit. At these temperatures, that steel bin might as well be a Tupperware container. That molten metal that we saw during the reaction was actually unoxidized iron. If we take a look back at the chemical equation, we see that iron is one of the products of the thermite reaction, and this is actually pretty pure. Now, by the time the reaction had subsided, this steel bin was being suspended entirely on a pillar of semi-molten iron. I'll leave you with two last safety concerns. First of all, when the thermite reaction is going, it's emitting lots of light in the UV range, which if you stare at it for too long will probably be harmful for your eyes. Second, the smoke that you saw coming off the thermite wasn't smoke in the traditional sense like you would get from a campfire. In fact, it was particulates of probably molten metal and a couple other impurities in the reaction. It's probably not safe to breathe this in. I imagine it would lead to some health problems, and I can also tell you from experience, it's not very pleasant to breathe in either. Whew. It's cold out here. That's all I have for today. I'll be sure to link a couple of references and documents in the description in case you want more information. Also, I'll be available down in the comments. And once again, as always, thanks for watching.